And we've discussed now the DMAIC process improvement cycle in detail. And you've looked at the Six Sigma roadmap and the problem-solving strategy used in Six Sigma, where here again we have the letter Y representing the outputs, the critical to quality parameters, and X is then the influencing parameters, the parameters that influence or affect the Ys, things in the process that will then change our critical to quality parameters. Now, before we start looking at how to calculate yield and process capability and looking at the statistics, we're going to run through this simple example. So let's say you would like to start your own peanut roasting business where you're going to sell packages of roasted peanuts to supermarkets and gas stations, for example. Well, you've looked on the internet how to start a peanut roasting business, and you've bought the equipment and you've started roasting and started making some sales to customers, and you can map your basic process flow as follows. First is the step decorating. This is basically when you're taking off the shells. And you can do this with a machine or just by hand. And then, of course, you would wash the peanuts. So you would remove the shells or any dirt or any dust. And then, of course, key is roasting. So roasting needs to be done at 150 to 180 degrees Celsius. They must be peanuts, you must make sure they're evenly cooked. You don't want to have them turn black. You don't want them to be burned. And it's also important here, the longer and slower that you do your roasting, the more flavor you'll have. You also, the next step would be the hulling. So this is then to get rid of this red sort of skin in the peanut. And then you would do the salting. And actually salting is fairly complicated, but let's just say we're going to sprinkle salt over our roasted peanuts. And at that point, you're done and you can package them up. So this is important. You want to put them into your pouches, that they're airtight. You want to make sure there's no moisture, and so that you can then sell them and they will have a long shelf life. So now, starting our DMAIC cycle, what are our customer expectations? What does our customer expect? What are the critical to quality output parameters? And you could say something important is the taste of the peanuts, the appearance. You don't want to have black peanuts. You want them to be crispy, so not soggy. You want the price to be reasonable, for example, critical parameters. And now we're going to consider potential Six Sigma projects for your business. And you can think of different areas. So for cost reduction, for example, we could talk about reducing waste. Maybe we have waste during this decorating. When we're taking off the shells, we're actually throwing away some portion of our good peanuts. You could maybe save time with the roasting so that you could produce more quickly. Then you could sell more and lower the price, for example. Roasting, we learned also, though, the time affects the flavor. You could try improving the peanut color or the peanut taste. Again, those are both to do with roasting, for example. We also learned that having crispy, not soggy peanuts was important. So you would look at these projects, you would evaluate the potential savings in each of these projects. And what we're going to pick here is that we found out that reducing the moisture content would generate for you the most savings, just for this example. So your critical to quality parameter is the moisture content in each or in a package. So you have a set unit that you're measuring. And so, the savings, what could that be? Well, anytime a customer gets soggy peanuts, they're going to send them back, and that's going to cause you maybe loss of that customer. If you caught the problem, had some soggy peanuts before they were actually packaged, then maybe you could do some rework, roast again, but this might affect the taste as well as your time and capacity. So But you've come up with this project, and now you're going to build your team, your project team. So you start then by measuring your critical to quality parameter, here the level of moisture. And we want to understand, for example, the average level of moisture and the variability of the moisture per packet. So we're going to design a sampling pan and take our measurements. And we also have set ourselves a limit here. We don't want our moisture in our packet to be greater than 1%. Again, this is an example. So now, next step in measure, we need to go into the process in more detail. Again, this is our overall process, but in each of these steps, we have specific machines we're using, we have specific times that we're using, specific temperatures, for example. Here was the 150 to 180 degrees C. We have operators, maybe it's just us, but we have definite parameters that we are looking at, and we want to look more carefully at our process to find these X influencers. Because we have Y as a function of X. The critical to quality parameters are a function of our input parameters. Now, in your business, you might be the only operator there, but in order to get into a more detailed process map, you would talk to the people on the floor, you would visit the production, you would talk to experts. If you're just your kitchen and you with the peanuts, maybe you would talk to the equipment manufacturers. You would look at what other options are out there, learn about the process. And then, of course, you measure your influencing parameters for your process. In Analyze, we're going to be formulating causal hypothesis. So, what happens if we change an X parameter? What happens to our Y? We're going to be then identifying from all our possible factors, the key factors, the critical few that will affect our moisture percent. And we're going to prioritize then different improvement projects that we think of and perform experiments to test our hypotheses. And so the idea then is, once we've come up with a improvement plan that will definitely reduce our moisture, we will implement this new process, and we want to be able to measure it again to show that we've reduced, for example, from this wide variability that we had before, where we have here too much moisture, to a much reduced. So this is the new here. And here's the old moisture distribution. Here we have, outside of our 1% level, still too much moisture, but a very, very small percentage of our overall production now that we've improved our process. And then we want to control this. So this is the last part of a Six Sigma project. We want to implement then a control plan. And this is usually with statistical process control. Here's an example of a control chart, which is in our second course, of course. And we would have then our control plan, come up with a response plan, what happens if there's some issue in the future in the line. And then finally, congratulate your team. So maybe it's you. You've reduced your moisture content. You know that you have no more problem with soggy peanuts. So you give yourself a pat on the back and look to the next project that you can work on to improve your process again. The learning objectives are to be able to discuss the impact of defects in a process, calculate process yield and parts per million, ppm, to discuss the importance of a low fraction defective per part for complex products, and to understand the difference between a defect and a defective part. This will also help us to understand the terms defect per unit, or DPU, and defect per million opportunities, or DPMO, and we'll look then at how DPMO differs from ppm. And finally, we want to discuss the importance of preventing defects. But first, what do we mean by the word defect? And so in this course, we're going to say that a defect occurs during any process when the outcome of the process is not our expected outcome. And what we mean by that is that the expected outcome is the outcome that we have specified in advance. It's what we want the process to produce. And if a defect occurs, then the outcome of the process will not be as we expected. In other words, a defect is a flaw or an error or a discrepancy. And just to put this into a little more visual context, here are some defects from my former work. Here we have some random defects, some particles that deposited on the semiconductor wafer. These could potentially cause the integrated circuit, the chip, not to work. Here we have also, same thing, silicon wafers with, here's some systematic defects. Here we have gouges, for example, in the film, or lines that are not printed correctly. They're also unwanted. They're not part of the specified outcome of the process, and then could cause a defective part. Now let's look together at a simple process for making crayons. The two basic ingredients for crayons are paraffin wax and pigment color. These are then mixed and stored in heated gallon tanks, which I didn't actually put here. And then they're heated, this is a storage facility, they're heated up very, very hot and melted, and then poured into a mold of crayon-shaped holes. And a single mold can make over 1,000 crayons at a time, for example. You then cool the mold, and then an operator will use hydraulic pressure to eject the crayons from the mold. And then they're labeled and packaged. And so a crayon manufacturer, a big one, could produce 2 to 6 million crayons in a day, for example. Now, why worry about a few defects? You're the manager of a crayon manufacturer. Out of 100 batches of paraffin wax and color pigment used for the crayons, an average of 1 batch does not match design specifications. When you find out about a bad batch, you need to scrap around 40 batches. But you estimate that the scrap costs are very low. In fact, the scrap costs for this 40 batches is less than 0.05% of the cost of goods sold, extremely small. So you say the problem is under control. Now, from a quality perspective, are there any flaws in your thinking? Let's look at this together. So here we see our crayon flow again. Now, a defect is produced somewhere in our process. Let's just arbitrarily draw defect occurs. And this leads to, in my example, to a defective crayon. Let's see, defective crayon. Defective product, or if we were a service process, it'd be a defective service. Where are our costs here? Now, before the defect occurs, and we just did this in the face-to-face class with the students, and they said correctly, before the defect occurs, you have costs due to the materials. Now, we said that's not so much in this example. Even when we scrap the batches, we know that it's a small amount of money. But where else do we have costs? Well, we have also the labor that went into making that crayon. So the people that we've hired for our process, they're there to make the products, and we're paying them for making parts that we cannot sell. Now, the other interesting thing is if we have a process where we have a high demand and we have a capacity constrained process, then we're using, well, in both cases, even if it's not capacity constrained, we're using up capacity on machines. We're using up the energy costs, for example, for heating up those the mixture. The molding machine, we're molding products that could potentially not sell. So the capacity is being used up. And this can be critical when we have a capacity constrained process, which means we need every single part of our capacity, every minute of our capacity we need to make good parts to meet the demand. So these, though, in this part of the factory, we've got internal failure costs. So, which, although they may be small, they're very real. Now, the other problem is that we have this defective crayon. I really didn't write that right, did I? Crayon. And this defective crayon might end up getting out to the customer. Now, in the case of crayons, maybe it's not that critical. It depends if there's something toxic in it or something, then it'd be critical. But you can think of this applied to to another product, like a car or like some kind of medicine. If that defective product gets out to the customer, we have, for example, warranty costs, liability costs. We could have, even worse, recall costs. We could, even worse, have the loss of reputation. And loss of reputation leads to things like lower prices. We're forced to sell our product at a lower price, or even loss of market. The demand will drop. And these are called then the external failure costs. And these external failure costs are often underestimated. So even if you're arguing that the scrap of the material is not that much, there's other things you need to think about. And one of the most important ones is what happens if that defective part gets out to the market. And there's one more thing here. Can you think of one more thing, one more problem? It's the idea that if you allow one batch of 100, so one batch of 100, you're looking at 1% of poor material. If you allow that, you are creating a culture, 1% defective are okay. And what we're going to see very soon is that even if small percentage of defectives can accumulate to very, very substantial failure rates for an entire process. And these are crayons. We just have a few parts. What if you have a very complex process? For example, as we said before, like a car.